Section 6.2 continues the idea of orthogonality, and we're going to look at orthogonal sets and orthogonal bases. So first off, what's an orthogonal set? If you just have a collection of vectors, it's called an orthogonal set if every pair is orthogonal. So in other words, remember the definition of orthogonal, it's if the dot product is equal to 0. Which gives us a theorem. Okay, we have orthogonal vectors. These have to be linearly independent, because if you think about it, every vector in there is at right angles to every other vector in there. So there is absolutely no way you could combine any group of the vectors to get one of the other vectors. It's always going to have a component that's different in there. It's going to be pointing in a different direction, if you can think of it that way. So you've got an linearly independent set. As soon as they're all orthogonal, as soon as it's an orthogonal set, it is a linearly independent set. That means that it's a basis for something. So it's the basis for the span of that set. So the theorem says just that an orthogonal set is a basis for some subspace. Which leads to the idea of orthogonality and bases. Okay, so we've talked about bases quite a bit, and bases being a linearly independent set that you can build everything in your subspace. But we've also seen that there is all kinds of bases. We're used to the standard basis, whereas 1, 0, 0, 1, 0, 0, 1, the standard vectors. But we've seen that there are infinitely many bases for a subspace. The one we're used to, well, that is an orthogonal basis. Every vector in there, so if we have 3 dimensions, 1, 0, 0, 0, 1, 0, 0, 0, 1, those 3 things, they're all orthogonal to each other. When we have an orthogonal basis, we get things that work out easier. Okay, so for instance, here is an orthogonal basis for R2. We have 2 vectors. Those 2 vectors span R2. You can build everything in R2 out of them, but they are orthogonal. That vector is orthogonal to that vector. U1 dotted with U2 is equal to 0. That is an orthogonal basis. And it doesn't have to be a basis for the entire thing. Any subspace that has a basis where all the vectors in the basis are orthogonal, that's called an orthogonal basis for that subspace. Why are these things nice? Well, when you have an orthogonal basis, some of the calculations start to get easier. Okay? So you can think about how much easier it is to you to think about things in terms of your standard basis over any other basis. Well, if your basis is orthogonal, a lot of calculations work out easier when you start calculating things. In particular, here is one of them, Theorem 5. We've seen how if you have a vector, quite often you try to find the coordinates of that vector in terms of your basis. And when the basis is not your standard basis, you have to do some calculations. Well, if your basis is orthogonal, those calculations are a little bit easier. So if you have an orthogonal basis and you want to find the coordinates of a vector, so you have a vector and you want to find the coordinates of that vector in relation to that basis, you can do it with this formula. The coordinates are that shouldn't be y, that should be w. The coordinates are your vector dotted with the first element of your basis divided by that element of your basis dotted with itself. So it gives you an easy way to get the coordinates of a vector, but this only works if your basis is orthogonal. So for example, Here we have u1 and u2. That's an orthogonal basis. So say we want to get the coordinates of that. Up until now, we would have to solve a system of linear equations. But now that we know this property and we know that this basis is orthogonal, that's a right angle, it's an orthogonal basis, we can do it a little bit easier. If you take v dotted with u1, that is equal to -7. u1 dotted with itself is 2. So there's the coordinates, the first coordinate. v dotted with u2 is 6. u2 dotted with itself is 8. There's our second coordinate. So there's v, and equivalently, the coordinates of v relative to b is -3.5, 0.75. Isn't that easier than solving the system of linear equations? Orthogonal bases give us a lot of advantages. Okay, now this leads to something called an orthogonal projection. The idea here is that if you have a subspace, you can think about it in terms of R2 or R3, if you have a subspace and you want to project a vector on top of it. So for instance, here, the red line, this line, that is a subspace of R2. Okay? U is a basis for that. So what we want, but when we have this vector v, -5, -2, the projection of it is, well, imagine dropping it down in a straight line so it's perpendicular to our subspace. This kind of breaks this vector down into two components. We have the orthogonal projection of v onto u, so it's kind of the shadow of our vector on our line. And then we have a component that is orthogonal to u. So you think about it, you take the orthogonal projection of v onto u plus the component of v orthogonal to u. What do you have? You have one component, the orthogonal projection, which is entirely in that subspace. You have another component which is perpendicular to that subspace. You add them together, you get your original vector. So you're taking a vector and you're breaking it down into its components. One component is in your subspace. The other component is orthogonal to your subspace. That orthogonal projection, we call it v hat. And there's a simple formula to get that, again, using dot products. So the orthogonal projection of v onto u is given by this formula. And you'll notice that this is essentially the coordinate formula that we had from the previous theorem. So for instance, we have v and u from our previous one. What do we have? V dotted with u, that's equal to 10 minus 4, that's equal to 6. U dotted with itself is 4 plus 4, which is equal to 8. So v hat is equal to 6 over 8 times u minus 2. So it's 3/4 of that, which is equal to negative 0.5, negative 1.5, sorry, and 1.5. That is v hat. That is the projection of our vector on top of our basis vector, or the line created by our basis vector. This is a technique that's used all the time, especially in physics, for taking forces, taking directions, and breaking it down into different components. Okay, so we've seen the idea of an orthogonal set. We've seen the idea of a of how it's really nice when your basis is orthogonal, we're going to take that one step further. An orthonormal basis is an orthogonal basis where the length of every element in there is equal to 1. It makes it even nicer than an orthogonal basis. So for instance, this was the basis we had before for R2, but you'll notice that the lengths of the lines are all different. You take this one, that's essentially the same basis. You've got your lines pointing in the same direction, but your basis elements are all of length 2. So this, the first one, is an orthogonal basis. The second one is an orthonormal basis because all the lines are length 1. All the vectors in your basis are length 1 or norm 1, which gives us another theorem. If you have an orthonormal set, so this is looking beyond just a basis. So any orthonormal set, so any set of vectors that are all orthogonal and all of length 1, you put them into a matrix. So you put them one right after another and make a matrix out of it. You are going to have this property that the transpose of your matrix dotted with your matrix is the identity matrix. Now, what this means in reality is that this is something that's used that makes some calculations a lot easier. So again, when you go to an orthonormal basis, some things become easier. Or sorry, if you go to an orthogonal basis, things become easy. If you go to an orthonormal basis, things become even easier after that. So for instance, that was our orthonormal basis. Our matrix U is that, just sticking our basis elements one right after the other. You take U transpose dotted with U, and this is an exercise you can do. Dot them, put them together. Sorry, that's not dot, that's multiplied. So the matrix product of UT times U is equal to the identity matrix. And then finally, theorem 7. If you have a matrix whose columns are an orthonormal set, so similar to the last theorem, and you have any two vectors in Rn, you get a lot of really nice properties. So that U, the norm of U times X, is just equal to the norm of X. In other words, this is a matrix that multiplying by it doesn't change the length of things. It's going to take a vector and it's going to twist it around and make it point in a different direction, but it's not going to change its length. Dot products stay the same. So if you have two vectors and their dot product, even after you multiply each of them by U, the dot product stays the same. And you can think about this kind of makes sense because norms lengths are very closely related to dot products. So there's kind of an intuitive idea here that if lengths stay the same, dot products should probably also stay the same as well. And then the third property just kind of follows from the second one, that if the two dot products equal 0, then multiplying by U and taking the dot product also equals 0. So this lecture has introduced the idea of orthogonal sets, and it's used that to create the idea of orthogonal basis, which is a very nice basis to have, and then an orthonormal basis, which is an even nicer basis to have. Orthonormal bases have some nice properties in that transferring, doing a transformation from your standard basis to orthonormal bases, things don't change in length. So we've seen how changes of coordinates before. it tends to not change the length of coordinates, which is a very nice property to have at times. It's used all the time in physics and especially, but in some other areas as well.